will talk about how it said the weekly Trapped Submanifolds. It is a joint work with Cunha, de Lima, and Santos from UFPI, UFCG, and UFPB Santos. Well, here is some summary of the presentation. I will talk about the trapped submanifolds. We call the Penrose concept of trapped surfaces in the horizontal around the black hole. The study of this trapped surface has importance as in physics and in mathematics. So, we have in this presentation, we're gonna talk about the results of submanifolds in GRW spacetime. Okay. And these results in the topics are some results is in 2016, Henrique de Lima, Fabio Reis dos Santos, and this is another dos Santos, and Velasco published uniqueness results for trapped submanifolds and marginally trapped submanifolds in Lorentzian. After that, in the next year, Alias, Canovas, and Colares proved uniqueness results for marginally trapped submanifolds in GRW spacetimes. And in the next year, Alias, Canovas, and Rigoli also proved results for trapped submanifolds in no hypersurface of the seed spacetime. This is just concepts in thought. Inspired on these results, we will present techniques of trapped submanifolds and weakly trapped submanifolds in GRW spacetimes. Concept. And generally speaking, we say that if a submanifold is away from the infinity and it is weakly trapped, this must be contained in a slice. It is also non-existent results and reduction of codimension results. Well, so for the concepts, for those one who are not acquainted with the concept of trapped submanifold, it is trapped submanifolds. A space-like submanifold of a spacetime is said to be trapped if the mean curvature is time-like. It is said to be marginally trapped when it is time-like. And it is said weakly trapped when these vectors are causal in the mean curvature vector. We have a different concept here for weakly trapped when we consider that the mean curvature times the mean curvature is non-positive. It will be a weaker concept of weakly trapped because here we need it to be causal, and sometimes when when the mean curvature is 0, it is not allowed since the 0 vector is a space-like. Well, but here we'll deal with this concept as in this way. Well, the product, the setting is given this way of the trapped submanifold. We already said, but we have two normals. We have a normal frame, a normal bundle, and we put locally, notice that it is locally a normal frame with a time-like normal and a space-like normal, which is N and Ni. So we choose them to be orthogonal to each other in order to be an orthonormal frame. Then we define also the height function, which is the time projection, that is the projection on R of the submanifold, and we have the support functions. Notice that the support function have 3 functions here. We only use the third one because the first and the second, they are defined only locally. Since we have a frame only locally, we can have it globally, but at first we only have it locally. So the support function also, it is locally. We have the angle function, which is also locally when we choose the normal n. If you change this frame, we have another function angle. Well, in this context, we evaluate the Laplacian of the height function and the integral of the warping function. Notice that this function rho, it is an ordinary function which depends only on a real variable. And we have the Laplacian of h, and we have the Laplacian of the whole and the integral of whole. And we notice that we only choose this integral in order to simplify the formula. We could use it, the Laplacian of whole, but it would have more terms. So we have the mean curvature can be decomposed in a locally with the normal n and the normal ni with these two mean curvatures. Have the mean curvature hn and hn. We have then defined according to in this way, locally. This decomposition is locally, but we have this decomposition. So we have a lemma, which is very important for our results. It's defined that on let U be a smooth function, that the Laplacian doesn't change sign. So if the gradient is L1, is integral, then U is harmonic. So it is what we're gonna use for our results. So we have the concept of strong null convergence condition, which is a inequality tree. When we notice that this inequality, the left hand depends on M and the right hand depends on T. So we the infimum on K, since both of them are independent. So in this setting, we have the law estimate for the H curvature on a space like submanifolds. We have the concept of trapped manifold is mostly for codimension 2. And in this result I didn't tell, but they are in codimension 2. So we have this submanifold, which obeys the strong null convergence condition. Then the H curvature satisfies this inequality. Here I didn't tell, but A, capital A, is the second fundamental form associated to the space-like normal, and alias to the time-like normal, and S is the second fundamental form associated to the space-like normal. So this normal and this. If you choose well the dimension, we have is the traceless second fundamental form. So in here is the mean curvature. These are usual, and I defined it happens locally. So we have the Amorial maximum principle, which is another tool, which is like a maximum at infinity. When we have that we don't have a point at infinity, so we have a sequence of points going to infinity if it's not convergent. So like that, it goes to the infimum, and the limit of the gradient goes to 0, and the limit of the Laplacian is going to be non-positive. He is non-negative, but here he is changing. If it is infimum, it should be, sorry for the typo, should be greater or equal than 0. So we have this concept, and this is our first result we use here, since the H is bounded, and we have according to the mean curvature is bounded. So if the inequality 5 happens, then it is contained in a slice. So it will actually notice that this norm of H minus this log prime, log of rho prime, it should be 0 too. We notice that if this infimum is positive and the gradient is bounded, then this inequality holds trivially, because we can choose any constant C. We can choose any positive constant C. So this hypothesis holds when the gradient of H is bounded and this infimum is positive. So for the proof, I will only put the sketch of the proof, not go to the details. but it goes to the form of the Laplacian of the hive functions. When we have this, we have that this will be non-negative, and using the maximum principle, here is correct because we go H is going to the supremum, and here we have this Laplacian is non-positive. So here we go, we have that this should be going to 0. So if this limit going to 0, therefore these infimum are 0. So when this infimum are 0, then we have the results. Since the gradient is 0, and then when the hive function is constant, then it is in a slide. Well, for the Amorial maximum principle, we only consider the weak Amorial maximum principle. In this case, that is when we don't have the gradient condition. We have only the Laplacian condition, the supremum and infimum condition. So this is a stochastically complete submanifold, manifold actually. Complete weakly future or past trapped submanifold which lies in a time-like bounded region of a GRW spacetime with whole prime non-positive or whole prime non-negative on sigma. If H is bounded in the condition 5 satisfied, then sigma is complete minimal slice. We have more than that a slice. It is a hypersurface of a slice, and moreover it is minimal. And this slice is also a maximal hypersurface since it is in a Lorentzian space. So we have the equation. The proof is a little bit similar. We use the Laplacian of the second formula of the Laplacian of the sigma of H. And we have this, when we evaluate that, we have this condition is non-negative, and we obtain the results. Consequently, we have taken account that this is bounded, and while this whole prime is non-positive, we get this will be 0, and therefore we have that all these constants are going to be 0, and it is a slice. We also conclude that it is constant. So when the sigma is constant, it means that the hive function is constant because it is an integral of a positive function. So we have this more reduction of codimension using the second lemma, which is that we consider the support function non-positive, and we have this hive function integral, then sigma is contained in a slice, and it is a maximal slice. If the submanifold lies in a time, here is time-like, but we can consider time-bounded region, that is a slab. It is between a slice T0 and T1, for instance. So we have this condition that rho is monotone, non-increasing. We can also use this integral and the Laplacian, and we have this condition. So the Laplacian, since the Laplacian doesn't change sign, it must be harmonic. So since it is harmonic, we study now the square of H, and we have this result. Since the square of 8 satisfies this, then it must be constant, since the gradient is 0. Therefore, it is contained in a slice. So this is an interesting result, and we have also interesting corollaries. If you have a future, there is no weakly future past trapped submanifolds which lies in a time-like bounded region of this. We cannot have trapped submanifolds in bounded regions of it. And conversely, we can state this corollary in another way and write it in another way. It's just the same corollary, but I decided to write in a different way. If there is a weakly future trapped submanifold which lies in a time-like bounded region of a GRW spacetime such that the gradient is integral, then this must be expanding for some T0. And past we have this. So if there is a submanifold, weakly trapped submanifold, then we know that this space time should be expanded for some region. And this region, of course, it is a region which intersects the trapped submanifold. So here we have some examples of trapped submanifolds in the Trapped space-time. When we have this is a model of the Trapped, and we have with mass and m, and we have this. Well, this is the model for the black hole, and we have the r is bigger than the critical r, and we have this for the spheres which are inside the black holes. So these spheres, they are totally trapped. So they are actually trapped, and if it is time-like, we can observe that it is, since dr is the time-like vector, it is past trapped, since we have a minus m. Actually, it is future trapped, since we have this. It is according to the sign of this. When r is small, then this is negative, and this is also negative, so it is positive, then it is future trap. So we have actually compact trapped submanifolds, which are these spheres. So in example 2, we also have another example for thoroughly geodesic equators of Sn, which are also compact, and the existence, since all compact, here I'm showing example because compact manifolds are parabolic, and parabolic manifolds are stochastically complete. So we are proving actually that there is stochastically complete manifolds which are trapped. So according to the sign of t, of the time here, we have that this submanifold will be past trapped. Actually here, notice that we have the equality for the second fundamental form, which we call thoroughly trapped. I didn't say, but it's related to the sign of t. So here in generally we have this in Eraldo spacetime, and have a totally geodesic submanifold, a totally geodesic hypersurface of the m sigma. We have this equality. So according to the sign of f prime, if it is expanding, for example, we have always a trapped submanifold. If this sign is positive, we have always past trapped submanifold. If it is negative, we have always future trapped submanifold according to the thoroughly geodesic hypersurface of M. So it is a simple way to find trapped submanifolds, future trapped or past trapped submanifolds according to the totally geodesic hypersurfaces of M. So we give another example here, which is not compact. The example here in the second part, we don't know if it is compact or not, but here specifically is not compact. We have this, it is similar to the Average-Rosenberg hypersurface. When we have this example, if we consider it is a surface, when we take off the last coordinate, and we have also the mean curvature, the normal, and the normal we'll choose specifically like del S, according to the last coordinate. In this case, we have this, they are orthogonal, this surface, they are perpendicular, we have constitute a frame, orthonormal frame actually. So we can also have this mean curvature. When we have this mean curvature, according to the sign of A, if it is positive, it is future trapped. If it is negative, it is past trapped. We notice that A should be less than 1 in order to, we have this square root. So this is our example. So we're showing that this example corroborates our theory because the hypothesis failed of some of the theory. And here are the bibliography we use it to make this presentation, some to make the results. Penrose's original paper, Lima, Santos, and Velasquez initial paper, and also we have also our result from Cunha, Lima, and Santos, and we have another result for standard static spacetime, which is published in Archive4. I didn't talk about that, but we have also that, and we have the paper from Alias, Canovas, and Colares, which was initial motivation for our results. So, muchas gracias por su atención.